Office to open the workshop.
Thanks, Lee, and thanks to all of you again for coming to hear about our update of the Delta Smelt individual-based model. Many of you attended the workshops we hosted last year to share our statistical models of the Delta Smelt life cycle. Today we're sharing a parallel effort we've been working on with Kenny Rose and Wim Kimmerer since 2017. Kenny and Wim, along with Karen Edwards and Bill Bennett, published the first version of the Delta Smelt individual-based model in 2013. And I want to extend a big thanks to Kenny and Wim for helping us with this update. Today we're having the first of two workshops. And today Kenny's going to describe the various updates, that we've made over the past several years and do so basically for a general audience. This summer in a second workshop, which we haven't actually scheduled yet, a specific date for anyway, Kenny and Wim will take a deeper dive for those of you who are interested in learning to interact with the model. So I think with that, I'm going to hand the platform over to Kenny and let him get started.
All right, well, everyone, thank you for joining. And I just want to note that it's 6 minutes after 1, so I'm definitely going to go past the 1:25, which would be 10:25, but we'll make it up later. So this will be 3 parts, and you're going to have to listen to me for all 3 parts. The first part is a general overview of what we're trying to do, and this is Wim has been on this since the beginning, and then Derek, Lee, and Matt have been heavily involved as we proceeded with the resurrection or the updating or whatever you'd like to call it of the model. But I also want to acknowledge people who've made major contributions throughout the development, and that's Bill Bennett, Karen, Rachel, and the gang at Virginia Tech who were able to do a Monte Carlo uncertainty analysis of the model. So this is part 1. If you stick around, I hope you do. Part 2 takes a step back even, and focuses really on, in general, how do you use these models to answer questions and interpret the results. And then I will sprinkle that with specifics about the Delta Smelt model. And then finally, part 3 is we're going to kind of go deeper into the Delta Smelt model and specifically blow up or expand on some of the processes and questions it has answered and perhaps could be used to answer. So a very general overview, because I always think it's important to kind of know how we got here. So we're going to talk about why and how we model. That'll be quickly. And then the DSIBM, we get tired of saying Delta Smelt individual-based model, as a platform where I think it's transparent, and that's something we can discuss, and how changes in hydrodynamics, water quality, habitat affect the population. And then I'll run out of time, and so I'll do 2 very quick examples, and then we're going to revisit a bunch of examples in parts 2 and especially 3. So if you really step back, what is modeling, right? Well, it's a way to look at a much simplified version of the real system, right? And we all do conceptual models, whether we realize it or not. The Delta is lucky, and it has formal conceptual models that people invested a lot in that are very handy. And then there's the mathematical ones, and the mathematical ones are an inexact science, as many people know. It doesn't mean it's not robust. It means that there's judgment involved, and that needs to be tested. So if you really, I gave a talk recently called Bay 101 here at the Chesapeake Bay, and people sometimes confuse this kind of modeling, simulation modeling, with statistical. So the way you can always tell is if you see a lot of rates of change in derivatives, you're doing simulation modeling. If you're looking at population size and how it correlates to various factors like temperature, you're doing statistical. So the modeling I'm going to talk about is actually differential or difference equations, which you then solve to get that bottom row of population size through time. But you formulate the model on the rate of change of the population. Something like, and when you look at your investment for retirement, you look at the total amount there, but you also look at what the interest rate is going to be and the return rate. And that's the derivative that we're interested in. Been lots of statistical analyses of the Delta Smelt in this system. These were ones I came across. There's many more. Statistical approaches, they have some great benefits. Standardized methods, very compact. People like them because you can compare them to data, and then you say they look realistic or not, and you can quantify uncertainty. Downside is they're mostly correlation based, and they have limited predictive ability when you create new conditions and you want to know how many Delta Smelt are going to be there. And then, of course, you can flip side and the simulation, instead of standardized methods, there's judgment involved. Instead of it being compact, you have the 4,000, 5,000 line Delta Smelt code. You can do a nice check on its reality. In the simulation, it's a little trickier. What do you include? What do you exclude? And quantifying uncertainty is also trickier in a simulation. So why do we do it? Because it's on a more mechanistic level, which we hope then lets us go to new conditions and generate better predictions than a statistical approach, and as well as to know why things happened. One confusing thing for people in simulation is they confuse complicated models with complex behavior. So I don't think you can get much simpler than that model there. X at n+1 is Rxn 1 minus xn. And those are 4 different values of R in that very simple model that illustrates complex behavior. Complicated models can also illustrate simple behavior. So don't confuse the complexity of the model with the complexity of the behavior. And why that was me some years ago. That's the picture they decided to post at the website. I looked a little exasperated at the time. There's science questions, there's management decisions. This audience doesn't need to be reminded of that. Why else do we model? Because there's only one delta. I wish there were 5 and you can, or 6, treat 3 and don't treat the other 3. That'd be a lot easier. And to make it more complicated, there's a lot going on, as people know in this audience, in this system. And so really all these things changing at once under novel conditions, some of them under extremes, droughts, etc. You really, the simulation approach offers some promise for that. So we really want to know where we're going to go. Is it going to be path A, B, or C? And a lot of times we use the past to do that, and it works sometimes, and other times none of the methods work because the future conditions are so different, and you have to just pay attention to that. Why Delta Smelt? I don't think this audience, you're probably tired of seeing these graphs and stuff, but they speak for themselves. This is the Delta Smelt index. Based on the fall midwater trial and the summer townet survey. We deal a lot with the life cycle. This is a life cycle published by Peter Moyle and others, but it's pretty much the IBM follows it to a large extent. And it's very important to think of life cycles when you're doing this, because you could do all kinds of things in one stage, and they may not have much population effect because of what happens in another stage. We're in a lucky situation in terms of conceptual models of what factors affect Delta Smelt, because this is just one page from IEP, an updated conceptual model, and these are the possible factors that could affect survival from juveniles to subadults, which occurs over the summer, it just gives you a sense that it's pretty hard to figure out statistically what's going on. I hope by the end of the 3rd module, you'll think this model can help pull apart, tease apart, deconstruct some of these possible effects. How do we do it? Well, the model can be simple or complicated. It's not like it's new math. It's very old math we use. The challenge is combining the physics, chemistry, biology, and the people. And so, we make assumptions, and that lower left means we better change something in the computer model because the rabbits are chasing the predator. And we also, a model is some idealized version of the real world. Whether you think Garfield is a version of a good or bad version, that depends. But we're always dealing with the fact it has to be a simplification. And this looks kind of like me and Wim at one point. I think you should be more explicit here in step 2, right? And we do a lot of that, and you'll see. And this actually is just a screenshot of the Delta Smelt code. That's some of the lines in the code, and so we're able to do all that and put it together. And you don't have to do that. That's what I do, and other people on the team like Derek, who painstakingly went through the entire code. Another thing that I want you to think about is that the Delta is not alone. These are systems I myself am working on that face very similar problems and very similar development of models. And so sometimes it helps to kind of look around and see what others are doing. And the bottom left is coastal Louisiana, Chesapeake Bay in the upper right, the Everglades, Columbia River. And then the lower left is actually a tiny fish that lives in a stream where it's as deep as your knee, and a similar IBM was developed there. So this particular IBM, these are 3 papers that go into gory detail with supplements and all that about it, and that's kind of what I'm going to base it on. We did a lot of presentations of this going back to 2003. So it's been well vetted, and it's still imperfect. And to give you an idea, when we started this, Wikipedia was in its first year, and the fall midwater trawl index was 603 for Delta Smelt. So it gives you an idea. And what we're going to talk about is what questions are good for the model, bad, stay away from for the model, and a whole bunch in between. So why do we do an individual-based model? It seems like a lot of work. Well, it is what is running around in nature out there, and it's the Lagrangian view. That is, we can follow individuals, what they experience over time, what exposure they have to habitat conditions, the cumulative effects of those exposures. And this particular model is spatially explicit, so we can look at effects of spatial variation. And overlaid on the spatial model is a movement model of the Delta Smelt. When we started this, I used to have to justify an individual-based approach. I don't have to, I don't think anymore. So what are the features of this particular model? Well, it's running on the DSM2 grid and uses the DSM2 transport. And every time you see a blue update, that was what the recent Fish and Wildlife Service project that's still ongoing, and this is part of it, we updated the model based on that. So now salinity and temperature are actually the DSM2 values. So you'll see an update there. I didn't put them all in, but because we really went through everything, but just to give you a sense of the scope of the update. So we follow individuals from birth to death. The young become adults, they produce young, they become adults. So we're not forcing any kind of recruitment or spawning. It's self-regenerating model. And one of the things that Derek was able to do was actually take calcium output, put it into DSM2, and then we can run the Delta Smelt model. So you can run calcium scenarios and see how Delta Smelt perhaps would respond. This is the grid. We added a box, things like that. So it's the DSM2 channels, but some of the environment is overlaid, not channel by channel, but rather in habitat or spatial boxes. So each fish, it grows based on how much food is out there in the box it's in and in the channel it's in. That's the zooplankton, and we updated that for this. It's a bioenergetics based for growth, so it involves temperature and weight dependent processes. Mortality is is stage specific. They can starve. We're updating the density dependence, and then there's an entrainment mortality, which we're updating because there's new information. So the model is now going on, when we first started it, Women I, 20 years. And so, you know, there's a lot's been done in 20 years or 15 years since we last kind of really worked on it. Reproduction is weight dependent, temperature dependent. So all this occurs in the model with individuals, and they release eggs, and we take those eggs and we follow them as various bookkeeping's horrendous, but as cohorts, and they become yolk sac, and they become individuals, and then they grow up and they produce eggs. And the movement is the particle tracking that's been done with DSM2 for the passive stages, not eggs, but yolk sac and larvae, and then a behavioral based on salinity we call kinesis. So we've updated the zooplankton in the model, where I was supposed to have updated entrainment by now, so I'm just going to leave that loose. I'll show you an example where we added a feature of supplementation. We've updated that you can, thanks to the efforts of Derek working on that a lot, calcium to Delta Smelt, and then many factors separately. So you get every day, every individual, you know their size, you know what they ate, you know their past, you know who they're, where they are on the grid, you know their box, you know their channel, you know everything about it. How do you summarize these? Well, we have a variety of ways to summarize these, and some of it is what you think it is how many are in each box on a given day. That's abundances, and we can actually sample the model like the TONET survey, the summer survey, the fall midwater trawl, the Kodiak, and we do that now. We do numbers and trained, and what's special about this is we actually estimate a projection model from all the individuals each year and get how that population, when it reached equilibrium under those year conditions, would grow, called Lambda. And if you take the geometric mean of the Lambda, it's how much the population, adults, would have changed from beginning to wherever you calculate n, what year. So it's all these calculations to come up with a single value. And it turns out it's been quite helpful if it's properly interpreted. So I'll show you a few examples, and then you'll see a lot more in part 3 if hopefully you stick around. I'll show you a food and entrainment question we had and a supplementation question that was posed. So on the left, that's a paper by Winder and Jaspy. There's been a lot of work done here. I tried to find a Kimura paper, but I wasn't able to on this, which, but as everyone knows, the zooplankton community has changed historically due to the influence of clam filtering as well as other factors. On the right-hand side, some work by Will Smith on entrainment at the pumps and estimating these annual entrainment values in a really interesting analysis. So a natural question is, which of these is more important to Delta Smelt? Has the change in food to the decline in recent years, or entrainment? So we made, I'll go into more details in module 3, but we set up the model as an experiment, and we put in old food, or we turned off entrainment mortality. By the way, turning off entrainment mortality may sound hard, but it's one line of code. Substituting old food conditions for new food conditions is a fairly extensive analysis. And what you see here is the geometric mean Lambda. So that's going to be the change in the population over the, what is this? I think this is 10 years, or maybe 15 years. I should probably know that by now. 10 years. And there's baseline, and it's A, B, C, D, E. What's that? Well, we addressed some of the uncertainties by saying, look, we don't know if there's density dependent mortality, and we have to worry about that, because if we put in higher levels under old food conditions, abundances may go up and maybe density dependent kicks in. So we came up with a way to do density dependence, that's B, mortality, I told you based on the stage. Well, maybe it's more continuous and based on their length. So we did that for C. We didn't like the results we got with old food. The larvae were doing worse. So we said that seems odd, and we looked at it. So we removed that effect by making larval duration a constant. So these are the beauty of this kind of model is you can go in there and do that. And then finally, we made maturity length dependent instead of a step function. And what are the 5 dots on the 2 left columns? There's 5 dots and 5 dots. Different year substitutions for 1995 to 2005. And we looked and said, okay, what was X2 in 1995? Let's find an early year before the decline in zooplankton that had a similar X2 pattern. That's that column, or an similar outflow. And we took the top 5 years because it wasn't exact. And now you can directly compare how much the population effect, abundance, lambda, would increase if you turn off entrainment versus had entrainment but old food present. And it makes for a very compact analysis if you think about what went in here, though. And then I'm almost there. What's a second example? Again, we'll revisit this a bit. This is now brand new. And you'll notice the baseline has changed. It's no longer 95 to 2005. It's 91 to 2012. I was asked to add a supplementation. Well, it sounds easy. An individual-based model, all you want to do is add individuals. This was very tricky to do, coding-wise, because of the bookkeeping in the model. We don't actually follow every individual. We follow a sample of them. But here's what the model can do. We do 5 events every year. That's the day we put the extra individuals in there, what box, what stage, their length, how many. And then we can run the model. And every year we do that, 5 events. And we see how the population growth rate would change each year. And that's the red line over the black line. And it's called strategy A because I thought I would have time to do B, but that's the only reason why it's called A. Notice that when there's some years where adding them doesn't help at all. And there's some years, particularly during the decline from 2001 on, where it does help quite a bit. Now you're adding ones, look at the recruits on the right, but you're not really helping the population in its growth rate because it's pretty much growing as fast as it can in those good years. So what we're going to do next, there's still more calibration, validation to do, and looking at the calcium. I'm focusing a lot on getting entrainment and some of those things that there's new information, getting that, make sure the model replays that to a reasonable extent, and also looking a lot at spatial distributions, which we didn't do previously. We did it very qualitatively. There's a couple of our interfaces being developed, one for post-processing and one for potentially using the model, and I'm not sure that's going to proceed or not. But otherwise, you just get these massive output files. There'll be 2 more sessions today. So the next one is uses, misuses, and interpretation of this model, and then digging a little deeper. And then, as Matt said, there'll be a really digging a lot deeper in the summer, where all the updates and how would you change things if you wanted to run the model, et cetera, is done. And so I'm not over by too much. And of course, the funding, some of you may remember CalFed. That's how far back this goes. Also, I was at Louisiana State University, and now I'm at Maryland. And then a lot of the updates and expansions and some of the stuff was funded by Fish and Wildlife Service. That's still going. So I will stop, and I think I stopped sharing.
Thank you, Kenny. Yeah. So we are going into question and answer section now. I saw Bob, you raised hand.
Yeah, just a real quick one. When you hit on the supplementation model and you said you added individuals, I'm assuming that you add the individuals as if they've survived the stocking. So because if you're kind of looking at how many we might have to produce, we got to take into the mortality of stocked fish is like really high right off the bat. And
Right. Yep. So, so this is, often I say, oh, it's hard to do this, hard to do that. That is easy to do in this model, because we had some discussions about what the questions were with supplementation. So the way I did it is you can tag. In fact, I do in the model. Every fish that was added is tagged, which means you can make its mortality different from the others. You can make its ability to feed different. You're allowed to follow those, and of course it's the young you're after, right? Because you don't just want to add fish, you want to add reproductive potential. So that is if you tell me that they have a higher mortality rate in their first 10 days, that's that. I don't say this often. That's very easy to do. They can even behave differently because we would just look up a different behavior. The key is you have to tell me. You can't just say they're different. You have to tell me how they're different. But that we can do. That's in the model now. To give them different characteristics. One thing we cannot do with this model is follow anything about hereditary traits, though. The way the bookkeeping is we mix all the eggs together into a big bin, and so we're not able to trace back to who your parents were. So,
thanks.
You can submit your questions through chat if you have. Yeah. Hi, Fred. You have a question?
Yeah. Hey, Kenny.
Hey,
first question
Fred.
is why do you look younger than the last time I saw you?
Well, boy, that's I don't know how to respond to that because it's so not true that I just don't.
Yeah. Hey, so real question for you. I just got a quick glance at the, your kind of preliminary results with the supplementation aspects of it. Is based upon what you guys have done so far, do your results suggest that supplementation is something that would have to be maintained continuously, or can you do it for a period of time and then have those benefits last longer?
So we again that's all preliminary. That was me doing it a lot to make sure the code was working right. Although the numbers are quasi, in the ballpark. I know that's also evolving. Given how long the species lived, I would, and now I guess there's always a disclaimer. I'm not speaking for the Fish and Wildlife Service and all that stuff. It would be hard to give it an injection and see a residual effect beyond a few years, unless you help them with better conditions as well, right? Because they don't go much beyond a year or two. So I would the way the code is set up right now. Of course, it can be changed, but it's set up to have an annual injection that you can change that each year, but it assumes it's going to happen each year. Now, coding wise, all we do is set it to zeros, and you can do a episodic one. And I did a few of those, again, mostly code testing rather than actually looking at what the results were. But it can be, but it's hard for me to imagine with this lifestyle that the Delta Smelt have, that unless, maybe you target really bad years, and you can put out more that way since they don't occur every year. Those are all strategies that can be looked at.
Okay, thank you, Fred and Kenny. We have Bruce.
Hey, Bruce.
Hi there. Thank you. That was very good. you answered my question, actually. I have two, so I get to ask a second one. But I was wondering about, does this suggest from your modeling that there's no real point in having it being done every year? And I take it from what you said that no, that's probably not useful.
No, I can't. I can't say that yet with enough confidence because I haven't tried other various combinations of life stages and timing and what box you put them in. So it is possible that the years I don't see a big effect, I put them in a box in which was basically at capacity, right? I have not explored why they are doing better in some years than another. My intuition says sometimes it's as good as it's going to get, but I don't have the results to really to back that up.
Displaying my own ignorance. When you change from year to year, how many things do you change? Turbidity, young striped bass abundance, whatever.
Good. So that's going to be coming up. The quick question, the quick answer is right now mortality is stage based and it's the same everywhere and every day if you're in a life stage. But this is, and we had discussions about this. If you can tell me what seasons and boxes you think predation is higher than others, it's very easy to put it in a model. But right now, predation is really a leveling factor rather than a factor that's going to create major differences. Now, when they grow slower, they stay in younger stages longer, so their cumulative mortality goes up, but that would have happened to them wherever they were. So right now predation is not dynamic and it's not spatial, but you don't have to model every predator to do that. And this is a discussion we've had with other people. You can tell me some years in some boxes you expect to see a lot of striped bass and other big predators, and then it's very easy in the model. Again, we know where every fish is every day. So if you're in that box and you're in that size range, your mortality just went up 20% that day. Cool. That's very easy to do, but it's not built in right now.
What about turbidity?
But I over the years I've really disliked turbidity more and more. So we actually I probably shouldn't confess this, but turbidity was in there and I took it out because it was on a different scale and there was a trend. And so if you say that mortality is higher in clearer water, I know what the model will do. So right now it's not in there. It can be investigated again implicitly. If you say certain areas, you just can't get too fine scale on me now. Don't tell me it's a 6-hour event, right? Because the model can't pick that up. But if you say that some months, some weeks in some boxes have higher or lower turbidity and it causes a reduction in growth or an increase in mortality or both, we could explore that. But
that doesn't seem difficult to me, but then I don't do it, so it seems easy.
Yeah. The turbidity, I think when this model takes its last breath, there'll be still this idea of turbidity. I'm happy to try again. Wim and I weren't able to do it, and I think Bill was involved at the time too. At the time we did this, but maybe now we know more. And
we've got good turbidity models.
So it may be something worth revisiting because it clearly is important to the conceptual model and to probably the dynamics of what's going on. And so it's not there. And which means when we talk about my next module, how do you interpret the results if turbidity is not there, right? It's so that may be something to think about if we could. Maybe the data are to the point now where we can do that and know what it's going to do. I have to know what it's going to do to to a process: growth, mortality, reproduction, or movement. I have to know that. So
we've gone a long ways down that road in the years since you started.
Yeah, yeah, considering it was 2001. So when we started, at least.
Thank you, Bruce. Kenny, we have two more people lined up. First one's Ted, and next Steve. Our time is already 10:40, so yeah, if someone or anyone you have question, please submit through chat. Next, Ted.
Hey, Ted.
Hey, Kenny. You mentioned how much the population has changed since you started this exercise, and maybe you're going to cover this in the next module, but any thoughts about interpreting the model output when, currently it's quite possible Delta Smelt can't even find one another anymore?
Yeah, so from a modeling point of view, we do not have depensatory processes in there. Although it's probably getting close. We might have more individuals in the model sometimes than are out there in certain stages, at least. That's a good question. I think one of the things, I'm going to give you an evasive answer. Just that's like a warning. It's coming. One of the things I think we would like to do at the end of this upgrade and stuff is probably put together a kind of a synthesis document from the modeling point of view, because it's kind of scattered, and then the model changes and it running different years, and I'm as guilty as anyone at that. It got better, but now what happened to the old results? When we identified some years ago good and bad conditions for Delta Smelt, is that still hold up when we have a lot more years? So I think I'm gonna evade that one and say that that's probably a topic for a very specific workshop, and it would really benefit by bringing in some of the other life cycle modeling that's going on with that, right? Because that you put the two together and you have a really pretty powerful. One's very data oriented, one's very process oriented, and maybe together you can really come up with. As when we first started, I didn't think they would get much lower, to tell you the truth. So I haven't. We need to do some of those simulations, and I think synthesis would be a good topic from that point of view. Was that evasive enough?
That was fine, thanks. I get it.
Okay, thank you, Ted and Kenny. And last one question for this session. I think that for the session 3, we have more time to have more question and answers, probably. Steve. Yeah.
Hey, Steve.
Hey, Kenny. Thanks, Lee. Great stuff as always. Big fan. Yeah, and I second Fred's. Must be the sea air or something out there. I second Fred's observation. So now I'm going to be really provocative. When are you going to be superfluous? Is this a kind of a tool that the community's ever going to have a chance to play with and ask of itself these very questions? You know what I'm saying? I understand what you mean. Research thing, but is there any point when the model is going to be loose on the world and we can run it in meetings that aren't modelers?
Yes. I don't know if you'll ever get rid of the modelers completely, but I think that was one of the ideas about, and Matt and Lee can give you more specifics, but yes. So I think there's even so Derek carefully went through the code and added a lot of features. There's this idea of it being transferred over to Fish and Wildlife Service, and there's other people who are working on a user's guide, I guess it is, and the code will be there, and so I think yes. The short answer is yes, but it is a complicated model in terms of the code, and so. I don't know if you'll ever completely get rid of me, but it is being gradually moved over. I don't know if Matt wants to add something or correct me or.
Definitely wouldn't be correcting. I guess I have the hope that, well, let's say hypothetically we had to write another Delta Smelt biological opinion. Probably could never happen, right? But let's say hypothetically. Those things usually use calcium as the basis for comparing scenarios, right? We would love to see reclamation and DWR feed us that full calcium through Delta Smelt model results in a biological assessment, because that's an exceptionally objective way for us to think about project impacts. So yeah, I would hope that the modeling community more broadly takes the model up, I guess, is what I'm trying to say in kind of a long-winded way.
Yeah, I would echo both Kenny and Matt. Yeah, we are planning for this model to be useful for most people, if not everyone. So yeah, stay tuned how that goes. Yeah, thanks. Okay, so our time now is already 10:46. So should we continue? How about Kenny? Do you want to take
Yeah,
5 minutes break?
No, let's continue.
Okay, let's continue. Hopefully, at the end of section 2, we have like at least 5 minutes break. Yeah. So okay, thanks, Kenny.
Yeah, I think that would be good. So hopefully you see the second one and part 2. So and there it is: uses of the model, misuses, and interpretation. So we're kind of now kind of tunneling down and being a little more specific, but not completely. Well, I thought there was going to be a break. You know the cast of characters and you know the history. So what was the purpose of this model? And then I'm going to, again, pull back a bit and talk about some best practices and concepts, and then relate it to the DSIBM, all in 25 minutes. But the idea, again, is let's say you comes across your desk some analysis that use this model or similar model. This is really guidance, and it's the world according to me. How I would sit there and say, how should I interpret these results, or how should I ask questions of the modelers or the people running the model? So we love to hate models, right? It's one of those things, and they're usually used for synthesis and understanding, hindcasting, projection, and forecasting. This model is in the realm of synthesis and understanding and projection. So we're not forecasting, for example, and what does that mean? I'll show you in a second. And where does this model fit on the universe of possible models? Right, and of course, this isn't the entire universe, but so on the x-axis, this is a paper we're in the Marine Ecology Progress Series about climate change predictions using bioenergetics. Is this notion of on the bottom left is environment habitat models, right? Then the individual DEB models, dynamic energy budget models. Species distribution models begin to move towards population, community, ecosystem, EWE, Ecosim, Atlantis. And so where we are is right in that green, right in the middle of the screen, called full life cycle IBMs. And we're kind of on the left of that oval where it hits population. So we're in fact not on the most complicated part of things, but pretty complicated for a population dynamics model. So others have said what is good modeling practice. Of course, I'm going to use what I said. I tried to name this paper proposed pretty good modeling practices, but that didn't go over so well. And this came about, by the way, a very similar thing in coastal Louisiana. People picked a model, used it, and everyone said, well, how did you end up with that model? And so we wrote this paper about it. So I'm going to quickly go through, and I'm happy to discuss this with people. And this is what I like to do at any time, I guess. Life cycles, you have to think about what is baseline? What are you comparing something to? you got to ask specific questions that are testable. You always think about what's being scaled in the model. Be very wary of explicit because it has a knob named turbidity doesn't mean it's doing what you think it's doing. Calibration, validation, what scale you're going to predict on, and then ecological effects and sensitivity analysis. So you saw this life cycle in the first module. This really is the context of, and it's how I interpret when I look at the results. Is I think about the life cycle and the rates and the durations and the survival rates of where am I doing my analysis? Where did I perturb the life cycle, and where am I seeing responses? And this is again the same slide, and this helps a lot too, because it says to me, well, what's in the model? How is it in the model, and what's not in the model, right? Non-equilibrium theory. So on the left is a theoretical. We tend to think of the top panel on the left graph that the population is going to reach some stable value and stay unchanged. It's probably the one case we never see. So we have concepts like bounded stability, episodic stability, regime shifts, shifting baseline, right? So how does that relate to the Delta Smelt model? Right now we have two baselines, and I haven't rectified them yet myself. One is a 91 to 2012 that we're using for calibrating in the first half, and then trying to predict the decline in the second half. By the way, that's not data; that is the model. So don't get too excited that it agrees that this is all model output. But we also have the calcium-driven case where it's present day configuration of the delta and its food, but the hydrology goes all the way back to 1920. So it's an interesting way to think of baseline. And right now, these are not very comparable on certain outputs. And so we have to figure out as a group, our small group, how do we, are there really two different baselines because it's different or not? So always think about the non-equilibrium theory. You can see it's the age one is the black line on the bottom right. That's not a stable, steady state, but you might say it's bounded, right? So you have to think about baseline because that's what you're going to perturb things on. And you can ask simple questions, but don't expect simple answers. So this is the oil spill, Deepwater Horizon, that I was heavily involved with. And what you see are the blue and red lines. That's red snapper. Those who know the Gulf of Mexico, it rivals the Delta Smelt in contentiousness and interest. And everyone was asking us the crash of the red snapper, and there's commercial and recreational landings for Hurricane Andrew, Hurricane Katrina and Rita, Gustav, and the oil spill. And well, that didn't change much. And yet others were talking about how the oil spill caused big percent changes, including red snapper. So simple questions are very difficult to answer. And partly because of ambiguity. So I would propose when you talk to us or me, I once gave a talk at the American Fisheries Society, 6 words we should ban. One of them was habitat. I don't know what you mean when you say, what's the effect of habitat? It's not a construct fish see. You're thinking of something, temperature, salinity, bottom type, food. So say that, and don't say effects. Say growth, mortality, reproduction, and movement, and then what life stages and where. And of course, the cartoon is, I think you should be more specific here in step 2, and that's now a very old cartoon that says a miracle occurs, but you understand. So there's a power in ambiguity in allowing people to think creatively, and too much ambiguity creates confusion and really untestable questions. So I ask you a question, tell me, or this could be general, what do you need? And we'll deconstruct it together, and then we'll convert it to the DSIBM in terms of inputs and processes and outputs. But please don't filter it because you think it's going to take too long. We don't have the computing power. The biology is not there, etc. Because I have to know what the ideal perfect cat looks like to see how imperfect I can get the model close enough, right? The turbidity question is a good one, right? So people asked what I thought was a simple question to me about supplementation. Well, we had multiple conversations. We had a call. I put out a couple of ideas, and then I think we got some pretty good clarity on it. But you would think a question is, well, what happens if you add fish? That's not testable. So always look at what question was being asked of the model. This is a figure about scaling. These are all processes that are occurring and how they affect growth, mortality, seasonal movements, etc., from millimeters in seconds to 10,000 kilometers in 100 years. And when I sit there with the experts on the system and the species, which I am not, this is how I'm thinking, what should I include in the model and what should I not include in the model? And it's judgment, but it doesn't mean it's weak. It just means you need to be aware of it when you're looking at model output. I can't tell you how many times I've sat there and someone says, "Oh, yeah, let's say the DSIBM. Yeah, I thought salinity would affect growth that way." Well, salinity doesn't affect growth the way you think it does in the model. So that can't be the explanation you see. It could be that salinity put them in a different place that had different food, but that's not the same as the salinity effect on growth. So always think what's in the model and what's not in the model. This is a recent figure I did for some people, from individuals to multi-year food web. We have, depending on your question, we have different blue lines for confidence, and we also have different red lines for how relevant it is to answering your question, right? We really have high confidence when we predict how a bunch of individuals in a box we force them at Delta Smelt, how they'll grow. How relevant is that to management's questionable, right? So you need to think about this in terms of what model you want to use, and then how relevant is it to the model that you have to do it. For the IBM that we have, you can't get too localized on your effects. We just I don't have the confidence in the movement and the responses and that probably box level is close as fine as I would get. I wouldn't get down to channels, and it can't be a box level for 30 seconds change, right? The time scale's probably got to be at least a week type thing, right? Explicit, implicit. Oh, this always gets me. Don't believe any dials you see on the model. We can label them as, when I code it, I can label it anything I want. Now I don't, but it doesn't mean when it's labeled salinity that it's the salinity effect you think is going to be important. So always look, what is it really changing, right? That's what's important. The DSIBM, we have a bunch of outputs. How did we do salinity? Well, we didn't go in there and add salinity to every box, every day, every channel. We contrasted population growth rate and annual egg production for high and low flow years. And then you go and you look and interpret and goes, well, what does that mean for salinity? So you see how much salinity differed between high and low flow years, perhaps by season, by key locations. Now you know what the change in salinity was you put in and what the response was. Implicit, well, we talked about this already. We can do a predation effect. I don't need to follow every striped bass in the Delta Smelt model, but I do need to know, I'm saying the modeler or the analyst needs to know how much, where, and when. And then it's pretty easy to do that. On the other hand, turbidity, I've still wrestled with, and now I'm based on the questions, I'm enthused again to try it again. Validation, the Delta Smelt model, if you're looking on the left for the classic predicted versus observed, you're going to be disappointed. That's not how you validate these kind of agent-based or individual-based spatially explicit simulation models. We do validate them, but it's not just as straightforward as what's the slope compared to the one-to-one line, right? And then, people don't like this, but, data are another model. And they have some distance from truth. And so we have the prediction, we have the observation, and we have the residual from that. But the prediction error is the prediction from truth, which we haven't observed. And so you always have to keep that in mind when you're making these comparisons. Of course, you still measure the skill of the model by how well it replays the data, but there's a tendency to get way down in the weeds of why didn't it agree Tuesday, March 12th, 2001 in this box. And that's not the validation of this kind of model. How are we going to do it? Well, we're going to calibrate to a relatively stable period and then try to predict what happens after that when the population declined. If you stick around for part 3, you'll see a whole bunch of comparisons that we do for simulations that are in those papers. This kind of validation makes some people uneasy because you really have to look at what confidence do you have each time you ask a new question. So it's messy, but it is quite doable. What's the prediction scale? So we use the term prediction to encompass the others. The hindcast is how you fit the past. How do you tell a projection from a forecast? Probably the easiest way to do it is look at the time axis. If it says year 1, year 2, year 3, you're in a projection. If it says 2002, 2022, 2023, you're in a forecast. So that's, if you want to know the weather, I don't think you're interested in a projection. You're interested in a forecast. The Delta Smelt model does projections. We don't have everything that's going to change in 2023 in the model. So it's really not, even though we get a little sloppy with the axis labels, but also look if it's relative versus absolute. Is it the number of individuals in the population or the percent change? I'd say all these kind of models do much better on percent change because it's to their baseline rather than to the baseline that's in nature. Of interest on an endangered species is also how many individuals are there. So you have to be careful how you interpret any of these results. What to look for? The spatial and temporal resolution of the model, of the changes imposed to answer the question. And then I call it the domain of applicability. I would have trouble looking at this model to look at 8 years of successive drought. It's just too far away from the conditions that we fit the model to. 1 year, 2 year, maybe should be okay if we have enough extreme years. So you have to go and look, okay, how did they put this in the model? How close is it to something the model has attempted to replay before? And then don't accept any projection that doesn't have an explanation as to why it occurred, because that reveals the hidden assumptions, right? If you make me explain why it happened, then you have a much better way to judge the confidence you have than just seeing a 26% change. It's 26% change because the larvae got more food, which changed their growth rate, which changed their duration, which changed their survival, blah, blah, blah. That, and then you say, okay, now does that make sense to me, right? Ecological effects. Statistical testing of this kind of model output's probably avoided. Why? I can take the same difference in predicted Delta Smelt abundance, just do more runs, and now it's statistically significant because I have more degrees of freedom. So really focus on the relevance to the ecology on the responses. And this is true not just for simulation models. There's a lot going on about, there's a paper by my friend Eric Smith recently. Stop with the significance stuff and look at effects. Look at effects. A very quick way to do this, always look at the scale of the y-axis when people are reporting these simulation results. That tells you the effect you're going to see, right? And every once in a while you see one that it looks like this large effect and it went from 0.7 to 0.73. And it's just because software scales things so it maximizes the difference. But always look at that scale. That'll tell you a lot. And then finally, sensitivity and uncertainty analysis. I think there's too much. Everyone says you need a sensitivity analysis. I think it's not the panacea that people think it is. I think they're confusing precision and accuracy. It may help with precision. It doesn't help with accuracy, because in a model, it will be most sensitive to something in the model. It has to be. And always ask with an uncertainty analysis, how did they get the uncertainty on the inputs? Everyone looks at the uncertainty of the outputs. How did they vary the inputs? Was it plus or minus 10%? Was it based on some knowledge? Was it based on different year types? I think the best way to do this is to think of the simulation scenarios as experiments, and there's an experimental design, and you take it, and sometimes we do factorial designs. Sometimes we do main effect designs. That to me is what the power of these models are, rather than varying the inputs a lot and getting a distribution of the output. It's helpful, but it's not the end all. So a couple of quick examples. Here's a design. What's the question? This was in the transactions paper too. What is the relative contribution of these 5 factors to interannual differences in Delta Smelt success? Okay. A weak phrase, Delta Smelt success. That first thing we have to define. We decided that was Lambda, population growth rate. So we do all these massive calculations to come up with Lambda. Right? Finite population growth rate. 1.1 means it would increase by 10% that year from where it started. We varied 5 factors, and we varied them 1 factor at a time in the leftmost column: salinity, temperature, food, hydrodynamics, and stuff. And how did we do this? How do you vary hydrodynamics? So what we did was we took a year in 1998 that Delta Smelt was healthy, had pretty good recruitment or high indice values, and we took a bad year, 2001, and we let nature set up our treatment levels. So the first column is each one. The second column are the pairwise. The third column is they're all 3 at a time, which means you're in 1998 unless 2001 1998 start at the top, and then you plug in 2001 for every time you see SH. So it's 1998 for everything but salinity and zooplankton, where we use 2001. Finally, you do all 4. You do 4 factors at a time, and now you can begin, even though it's a very complicated figure, to figure out how Lambda went from 2 point something in 1998 in the model to about 0.4 in 2001 at the bottom. Which of these factors and which combinations were getting you there? And you can read the paper or you can ask me. And I think we did a pretty good job at identifying not only the individual conditions, food, salinity, flow, hydrodynamics, temperature, but also the combinations that actually, each one may not look so bad, but together they're pretty bad. And then 3 at a time. And of course, this would be impossible to tease out from field data. And it was tricky to do it here too, but you can do it in this kind of simulation environment. And then finally, for the second module, what is the relationship between Lambda and variability and the key model parameters? And I'm already going to, boy, in one talk, I violated my own guidance. I'm not going to tell you how much I varied things. I just wanted to say the top left there, a lot of people told me, the problem with these IBMs is you can't do Monte Carlo uncertainty analysis. So my real goal was to do Monte Carlo uncertainty analysis. And we ran the model thousands of times on a big supercomputer, and it actually wasn't as hard as it sounds. It wasn't, of course, I didn't do it. They did it, the people at Virginia Tech. And you can tell where we published this, Annals of Applied Statistics. But the idea was a very sophisticated Monte Carlo analysis of this IBM, where this is the results. You can see log of Lambda, that's the geometric mean over those years. We varied how well the juveniles feed, and we varied their mortality rate, a bunch of other things. And you can pick up these non-linearities, not only in the mean of the geometric mean of Lambda, but in the variance over the years that went into the geometric mean. And you see some really interesting non-linearities in the response. Oh, what's the model good for? Interannual variation, questions about flow conditions, good and bad years, different types of years put together. Anything DSM-2 can handle, we can do, and we can do some tweaking from that, but that's fundamental. Growth effects, the growth model has held up quite well. And it's the timing kind of things on weeks to months to seasons, the phenology of events, when they migrate, for example, in the model, that kind of stuff. And then we can even go in and give some of the individuals, make them stay in fresh water and make the other ones move and all that. What's some stuff that's good, but we need to, tread cautiously and make, dot the I's, cross the T's, make sure we're doing all this right. Is predation effects. Some wrongly say it's not in there. It is. It's just a constant. So if you can tell me enough information, we can put it in there. I see turbidity. I bring it up all the time. I don't want to talk about it anymore. And supplementation. What's the model not good for? Highly localized short-term perturbations. You can take a piece of the model and do that with it, but not the IBM as the IBM. Heritable traits. I'll give you an example. We had the model was density independent because the population's low, and we said let's put in those early food conditions. We didn't know how high the population would go. We looked at the fall midwater trawl, and it could go pretty high. So there was a missing process, density dependent mortality. So we put that in the model in order to answer what would have been a bad way to answer the question became a good way. And how did we put density dependence in there? Well, we can trick the model and we can force egg production and have mortality rate of every juvenile every day be dependent on how many other juveniles are in their box and generate a spawner recruit curve on the bottom and then assess that against either the field data or what people think. And so now we have a version that has density dependent mortality that kicks in when the population gets relatively high. So then we could then address that question with a lot more confidence. Okay, if you're still with me, next is part 3, and we're going to dig a little deeper. And I'm going to, in case people joined in the middle, I'm going to thank the original funding and especially a lot of these updates from Fish and Wildlife Service.
Thank you, Kenny, again. So we are going to open the mic or chat for questions.
How much did I go? I have a question. How much did I go over?
Yeah, no, it's 11:13. So.
Oh.
Yeah. I think. Yeah.
Yes. So we're supposed to be done at 12. Okay.
In break. We're supposed to be in break this time.
That break thing didn't work out, did it? Okay.
Okay. So let's see if there is any questions from participants.
Lee, Ted had the question about the Marine Ecology Progress Series paper. I don't know if Kenny saw that.
I did not.
Yeah, I can send you email after this, and you can forward that to me. Yeah, I can send it out.
Which one's that?
I think it was the in review one, so I'm not sure it's ready to be shared. That's
that one. I can certainly send you the draft we submitted. No problem.
Okay.
I was thinking I don't remember putting a Delta Smelt paper in MEPS, and so I remember that.
Okay. Thank you. Yeah. Okay, so there is question on chat.
Okay.
Do you want me to read, or Kenny, you want to see?
Yeah, it's probably be easier. I haven't been keeping track. Well, I see. Yeah. Did you want to read it so everyone?
Okay, I can read it.
Yeah.
The question is, how easy would it be to copy the code and apply it to other threatened species like longfin smelt? would it be starting over from the beginning or changing a few lines of the code?
No, it's not. You can use a lot of this code and approach for long fin smelt, but it is, I assume you're going to go out into the bay. You're really going to change the grid to, but the approach, I've suffered, and Derek has too. We know how to code this now, so that, and we didn't when we started, by the way. The whole bookkeeping. So the bookkeeping remains. That's independent of the grid of the species. It's pretty easy to adapt that, but it would be. I would probably, if anyone has seen my code, I would probably start with a clean slate and then move stuff over so that I know it's all correct. Put it in. Okay, this is how we're going to do the bookkeeping. Let's test the bookkeeping. Okay, this is bookkeeping for longfin smelt now. So do they spawn twice? Do they spawn 3 times? Do we have to, I would do it that way. So it's far from changing a few lines, but it's also pretty far from starting from ground zero.
Kenny, can I add something to that?
Yeah, sure.
Yeah, so one thing you'd have to do is you'd have to use different hydrodynamics. It wouldn't work with DSM-2, which I think would greatly complicate things. Although, right now the DSM-2 run is outside of the IBM, particle tracking model is within. And so the particle tracking model would have to be changed, which brings in quite a lot of additional complications, apart from the difference in biology and the fact that they go out to sea and disappear.
Yes. So yeah, absolutely. The only thing I could say that's a little bit optimistic is I've done these models in ROMs, FVCOM, MOM, in 3D, and so but absolutely, Wim. Yeah, you're really what you're really grabbing that we learned is the algorithms, and then putting it into a new system, and so that saves you time. But let's just say it's not a week's worth of work. It's more than that. I should say a lot more than that.
Yeah, if the focus is still, for longfin would still be effective freshwater flow, you have to somehow tie one of the 3D models into calcium output.
Yeah.
I don't know how hard that is.
Okay, thank you, James White from Fisher from CDFW for the question. And I think probably this needs to be discussed maybe another time. More details could be, yeah. So thanks. And are there anyone who has any other questions? I would like to read a comment from Steve Corbison. Kenny, this module 2 is the basis for what I think consumers of models should know as the bare minimum. I don't think you can have a productive discussion of model outputs without these things in mind. Model consumption is a dialogue in my mind, not an answer.
You could have saved me a lot of time just by saying that, and we could have skipped the second part.
Yeah, I like this comment. Thank you, Steve.
So there's one more module.
Yeah. Do we want to move to next one, or what do you think?
I
Kenny?
can.
Okay.
It's okay with me.
Okay.
And I can't tell who leaves, so it's okay.
Okay, go ahead. Yeah.
All right. Let me move that over so I can still see people. Okay, so part 3. So let's go a little deeper here. And remember, there's a whole nother workshop planned for that. Well, you don't need to see that anymore. So we did the overview. We did some guidelines. Now let's really see what the DSIBM can do. Some of its structure and some of its example results. Yep. Now, so Wim and I were happy. We were, I think, I know Wim was cruising to retirement. I'm still working, and then the idea was to update this, expand the model from what we had ended with these 3 papers with, and a couple of others, but and so that's what we embarked on. So what you'll see is periodically you'll see an update, which means that was part of the update. Most of the results, not all, are from the old results, because I didn't want to put out results until we're really happy with the calibration, validation, and all that. And we're not done with that yet. The entrainment, the new way to do things, the new food. So it's kind of a mix, and I apologize for that. So it's, as you know, it's DSM-2. One of the updates was it now uses the actual salinity and temperature predicted by DSM-2. So it's the complete salinity temperature transport package from DSM-2 is what the individuals experience. Since I had this idea people would come and take breaks, so I don't need to repeat this part. And we have now a flow diagram. So this gives you an idea. So you set up the model, you have initial conditions, and you loop over years. And you know, what kind of year is it? And we use specific years. In fact, we go 1920 at this point on. It gives you the information on temperature, salinity, transport, and now note the zooplankton still come from the field data. And so that's very important when you interpret some of these results. And then you loop over days. By the way, every IBM pretty much does this. And then you loop over individuals, and almost every IBM is a series of nested loops. And you keep going over individuals, and then you go over days, and then you do the next year, and you keep going over and over again. You know the grid by now. And zooplankton, right, is by box now, and salinity and temperature are by channel in the new version. So this is just to give you an idea what's going on. So this was that 98, 2001 again. Remember, we have a temperature for every day, for every box, for every year. And we have a salinity value for every box, for every day, every year. No missing values here. The update was, these are now from DSM-2. We have food. And that's why I say this model's, I think, quite good at feeding growth-related questions that you want to look at. Again, every 98, 2001, each box, notice there's some, that looks a little stair step. We actually smoothed that, with this is Wim's work, in particular, his wizardry with the zooplankton data. And we've had, it's hard to believe it, after 30 years, we still speak to each other. And the zooplankton was challenging though, because it is complicated how we did it. And the workshop in the summer is going to go through that, because it is important how we figured out a way to do that, because it's very important to the model dynamics as well. So that's part of the update. So what happens? So you have a female, they release eggs, they develop where the female released it, and it's temperature dependent. Then they hatch into yolk sac, and that's temperature dependent. And they also die at the same time. They become larvae in exogenous feeding, and at 15 millimeters, they become post-larvae. At 25 millimeters, they become younger. They are juveniles. And then at age 1, January 1, they become adults. This also affects the interpretation a lot. So this is like where you have to really know the model, and it's documented, but you have to think about it. Juvenile survival is artificially ends, not when they reach a size, but January 1. And so that affects how you interpret things. You still can, but it affects how you interpret things. We follow them for ages 1 and 2, and then maturity either is a step function or a logistic looking function. And each individual gives a temperature. We accumulate and based on their weight, they release eggs, and we accumulate them on 14-day cycles and then inject them into the model. Individuals, if they're happy and there's enough time in the environment conditions, particularly temperature, they can spawn a second time. And the eggs were where the females were. The update here was we fine-tuned the timing in the bookkeeping. Working a lot with Derek on the code. I hope he now sleeps through the night and doesn't wake up in the middle of the night yelling something about what I did in the code. The bookkeeping is tricky. Now, so then they go and now they become yolk sac, and then they become larvae and they start feeding. And we went from 6 to 12 zooplankton groups on that reanalysis in the update. It's a lot. Gives us a lot more flexibility how we look at other food conditions for certain questions. Before, you had to map it to the 6 that were in there. So this is what the bioenergetics looks like. This is their net growth. There's their consumption. If you're a larvae, a post-larvae, lower left is juveniles, bottom right's adults. So this is scope for growth. And these are the components, temperature, allometric relationships. But how do you know how much consumption you get? And now we do that every day, every individual in every channel. They look at the prey that they have. They look at the prey that they like. They look at how good a feeder they are, and you get consumption. So once you know consumption and you know temperature and size, you can figure out their growth rate. Mortality is an instantaneous rate. And we have an entrainment mortality that we're going to revisit. Will Smith has done some work looking at the entrainment and has shared that with us. And so we're going to update the model for that. Movement. Now, movement's probably a tricky one. So the yolk sac larvae and post larvae are in 3D, but they're not really 3D because DSM2 is really up and down, upriver, downriver, and then the lateral and the height are kind of calculated from that using functions. Juveniles and adults are simply where they are in the channel from the beginning of the channel. So every time step, we update their locations. So we use the PTM to update hourly the yolk sac larvae and post larvae, and we do kinesis. So movement is where I've spent most of the last 5 or 7 years working on. And it's the most fun because sometimes these organisms are just so clever, it's really hard to codify their behavior. Right now in the model, it's based on salinity and it's updated every 12 hours. And so what does kinesis say? Kinesis says they don't know what's around them in the environment. They only know where they are, but they have a memory to what happened the time before. And if they're happy, so they're in 0, they're in, I don't know, whatever it is, 0 to 4, 0 to 6, 2 to 6. I forget which runs these are, but they keep going what they did. So when you take an inertial velocity, that's simply yesterday's velocity. That dominates when you sum up inertial and random. When they're unhappy, then random dominates, and it looks like they're wandering around. Now, in this case, they're wandering around in 1D space, but they're still wandering around. The update on here, what we're going to do is do a lot more comparisons to the survey distributions, fall midwater trawl, summer tonet, 20 millimeter, and Kodiak. in terms of spatial distributions, and we hadn't done that before, and we're going to do that now. I think I see a lot of questions being asked into the future, and I want to have more confidence that the model is doing a pretty good job spatially, more than I confirmed before, which was pretty qualitative and and eyeballing. So I want to make sure that it's doing that. These are just some of the stuff I've been involved with movement, and it's fun. It's my son calls that stuff when he comes in and looks at it. He calls it it's fish video games with bad graphics, and it's fun to watch. So what are the numerics here? So it's coded in Fortran, and the code's been checked extensively by myself and by Derek, which is great. And Derek in his revisions to it and its corrections got the code to speed up quite a bit. So we do super individuals. We do about 500,000 because that gives us convergence for most cases. What do I mean by that? That is super individuals is an approximation as if you followed every individual. So it should converge as you follow more and more super individuals, and eventually you're following every one of them, right? And it's kind of interesting. When we started this was a computational challenge. Well, I have a 5-year-old PC behind me. It's a big PC, but it's 5 years old, and it's down less than 3 minutes a year now for simulations, which is pretty good. It's not as limiting. There's 12 processors. I can do 10 runs at a time at the same speed, and I also can run it on big computers if I want to. So what do we look at? So this was newly analyzed. So this is outside the IBM. This is in R, and this is WIM's magic of kind of pre-calibrating the growth rates. Remember that functional response. You needed to know how efficient they were, K, and what their diet was, what they like to eat, the vulnerabilities. And so we do this outside the model since we can force them to stay in a box, and how would they do if they stayed there for their whole life stage? And that's kind of a way to calibrate. Excuse me. How do we calibrate the movement? So the way I do algorithms is I not only do I check it line by line, but I give it a problem where I know the right answer, and it should generate that. So here's a case where in the code you fix salinity in different boxes so that the confluence is ideal and the others aren't, and you don't kill them, you don't grow them. It's just following them with their kinesis movement, not transport. So it's not particle tracking. And you see how long and how well do they find the two value of salinity of 2 when everything else is controlled for. And then you always do this. I always do this. You flip it on them, and they should flip, right? Otherwise, all I've shown in the top is they like the confluence. Now make the confluence bad, a high salinity, and the other upstream and downstream good, and then you notice they're avoiding the confluence and they're going to the 2 extremes boxes. So that's how we work with and we look at the rate at which they do that. That's how we work with testing the movement algorithm. So you get baseline results. This is the old baseline, 95 to 2005. We have 2 new baselines, just to maybe, and we have to straighten that out. Remember, it's a Lagrangian view of the world. So we know every individual, every time when its location and the salinity at that location. So we can calculate the weighted salinity of the individuals by year. And then at the bottom is the field data done that way over the 4 surveys. And we're looking did we have them seeing the salinities that the field data suggested they should see by year. And you can stare at this for a while. I have. We can also do things like look at different outflow values and say what proportion of them are seaward of the confluence by year for different life stages. And the bottom right is actually the observed proportion of the fall, mid-award, or trawl seaward and what we did the same calculation in the model. And that's the closest I think we'll come to a predicted versus observed thing. So again, don't worry about all these details, but don't think that because you don't see an obvious validation, it's not validated. But it takes some work to assess what confidence you have with all these different checks. Here's the entrainment output. Again, we're going to look at this again, and the top right is the number of adults entrained each year divided by their January starting population. And there's some data. This was the level of comparison I did before. We can do better now with Will Smith's work. The left-hand side's larvae, and the top is the model. At the bottom is the data, I believe. It's been a while. I love these. These are life stage survivals. So this is what I use as a diagnostic tool when I try to answer a question. I perturb the model somehow. I put in a good year, put in a bad year, and I look at these stage survivals by year. Eggs, yolk sac larvae, post larvae, juveniles, young of the year. That's the product. Age 1, age 2, everything. And it really tells you a lot. And then you start digging deeper. Well, why was larval survival higher like it is in 98 here compared to 2001? What was different about it? Excuse me. This was the extent back then. By the way, the Kodiak trawl was new when we started doing this stuff. Now, Leo and the group and Matt and Leash, I don't know what they call it, unit, shop, lab, have really done some work on estimating abundances from the 4 surveys, and they've shared that with us and with me. And now I'm going to look at how the model's doing with that. I'm a little scared to do that though, because I'm not sure the surveys are consistent, but we'll find out. By the way, when it doesn't fit, that's when you learn a lot. Of course, if it never fits, that's not good. But periodically, you're going to get a misfit, and that's the interesting part of things for me. Remember, we take the IBM, we actually estimate a matrix model and calculate lambda. And so that I will say this because I think it's really clever how we summarized all that output. But lambda does not depend on how many fish are there. And it's an equilibrium calculation. So you have to be a little careful about it. You can get a high lambda with few fish. You can get a low lambda with a lot of fish because it's all based on rates, right? Okay, you saw this example before, right? Different years. Again, good years, bad years in a design. A question that we had to do that. What are the effects of entrainment? Another question versus the shift in zooplankton. You saw that. What I didn't show you in module or part 1 or 2, wherever it was, is how did we get the replacement old food in there? So what we did after much discussion was we would look at each year in the model. So look at the far left column of that table. Remember the simulations I'm showing you now are in that paper. I didn't want to show you the new ones. Some I have, some I don't. So in 1995, or let's take 1999 in the model, what years prior to 1990 would be good years to match with that? So we would use the zooplankton from those early years and hope that, you know, it's somewhat consistent with everything else in the model, salinity and all that. We're not changing those. So we did it by looking at X2, and we did it by looking at outflow, and then took the best 5 matches. And so we did like a sum of squares for that year's outflow and 1999. So on the right, you see how we substituted. There's baseline, and if you look at 1999, we used 75, 73, 79, 80, 81, and there's 75, 73. Yeah, it's close. I don't know why 79 is not there, but oh, we're replacing 99, but 79 should be there. So the black is the 6 zooplankton groups. We now have 12, and the blue are the replacement values. So you can see now what the increase in food in zooplankton was when we looked at the old versus the present day, the 1999 values. And we get these. We also weren't sure about some of the formulations in the model. We just go in and we try other ones. If we have the information, we can do it. It's not that hard. This is what you generate. So now we have 5 alternative baselines. That's 5 rows. We have the leftmost is when you turn off entrainment mortality completely, and the red line bumps up compared to when you have entrainment mortality. The middle one is based on outflow, and the right one's based on X2, and that's why there's 5 dotted lines, because we weren't sure exactly which year to go. So you can see the effects, and you can summarize it like I showed you this figure before with the geometric mean of these lambdas. The key, though, is why. Why did it happen? And that's what we do in the paper, and you should always expect that from these kind of models, is why did it happen? Well, it turns out they grew a lot better, which made the age ones more mature, a higher percent mature. Eggs per recruit increased because they were heavier, and therefore population size increased. Now, why do the red and black overlay each other? They should, because all we do is turn off a mortality effect. That's not going to affect length, fraction, mature, or eggs per recruit. Could affect eggs per recruit a little bit, but not much. So that made sense. Now, when you look at population size, you do see the red without entrainment higher than the black solid. Now, the other ones did have cascading effects through the food signal. Finally, we took this model and did an optimization on it. What do I mean by that? Well, we said when they want to recover this population, cost is an issue, and most bang for your buck, right? So we put it into an optimization. I guess you can call it a decision support tool. That seems to be a common thing. I'm not sure. And we said, what do you have to change in the matrix model each year to get lambda above 1? And that's that. So baseline's black, the red, green, and blue are different optimization schemes. When costs are low, red, costs of doing it are medium, high, medium, green, and high blue. So you can get there except for 2001. Very hard to get there in 2001. And what knobs were we turning? Well, we were turning age 0 survival, so you could think how you would do that. Age 1 survival, increasing their spawning, and then increasing their fecundity, which you think is giving them more food, right? The others may be reducing entrainment is one way to get that survival up. And these are how much these would have to change in that optimal solution. So it's the same 3 colors. And it would get you lambda above 1 and at different costs. So here's an example where we remember what we're doing. We're taking the IBM, we're using the every year's matrix model, and we're doing a formal optimization on it with a control rule. And then optimizing with that. And it's minimizing. So we give it a cost if your lambda's ecological cost if lambda's below 1 each year, and then we assigned arbitrary costs to how you change these different survivals. We weren't really sure, but we can plug in actual numbers, and you want to minimize that difference, right? Optimization can always be minimized or maximized. Finally, supplementation, and you saw this before, part of the update, and we had questions about that, so I won't belabor this, but you're already seeing interesting patterns I wouldn't have predicted of lambda responding in different years than recruits. And I have to think about that some more. Here's the output. If you take the CalSim simulation that imposed roughly the 2008 biological opinion, or it's roughly because I think it was as it was written in the opinion, it imposed it. And then you go over 80 years of hydrology with the current delta. You run that through DSM2, you run it through the DSIBM, and you predict how many Delta Smelt you'll be on January 1 each year, and the Lambda for that year. And these are the dynamics you see. And so that was quite I didn't do this, so I can say it was quite an accomplishment to wrestle with those coupling these different models. And I showed you the uncertainty stuff before, mainly because people said you can't do it, so we went and did it. I won't say it was easy, but Boya Zhang, was her dissertation work at Virginia Tech in statistics. So at that point, I think I could sense over Zoom that people are saying, please no more, I've had enough today. And with that, I will just end with not today, but like I said, we're still working on it, but much progress has been made. And you can see what we've been doing. The R interface is entrainment to survey industry, spatial distributions, baseline, et cetera, the post-processing. And then if you really want more, we're going to have a workshop this summer, and the format, other than I know we're going to go into kind of how do you actually run this thing, the format is maybe we're not restricted under COVID by then, and we can do this like a real workshop, which would be great, how to do that. So for the third time, I'm going to acknowledge Fish and Wildlife Service. Thanks.
This is great. Thank you, Kenny. We already got 2 questions through chat. I think the first question is from Steve Corbison. Yeah. Also, Wim already replied, so I don't know if we want to just use your voice to answer, so people calling in from phone may hear this.
I don't know. What did you say, Wim? Oh,
I forget. I went on to some length. So Steve asked, what advice or request would you have for data collection schemes for zooplankton, say, as a result of your experiences trying to use environmental and food data? And so I kind of homed in on the zooplankton part of it, and basically said, you know, that really there weren't many difficulties with the data, but the things that are missing are more data for the cache slew area. That was one. The second one is we need biomass, and we get counts. So for some taxa, we need length-weight relationships and lengths. You know, so in other words, this would require more work on the part of the monitoring agencies, well, part of Fish and Wildlife, to actually measure things that they count instead of just counting. It's more work, but the data would be much more valuable for this and for lots of other purposes. And I didn't really talk about the other aspects of the model that we could use better data for. You know, we've been kind of perplexed about how to bring turbidity into it, but I think that's not a data question. It's a mechanism question. You know, how does the, I mean, there are theories, but how does variable turbidity actually influence Delta Smelt? We don't know that.
Yeah, I didn't discuss that. I probably should have, but and the good news is at the summer workshop, which I really hope is much more of a hands-on workshop. You don't have to listen to me so long. Wim is going to have a speaking role, so you get to hear from Wim on this.
Okay, thank you both of you. Yeah, Wim and Kenny. Also, thank you for the question from Steve. Yeah, let's have 2 more questions through chat, and then we're going to have microphone open. Already, I see a hand already raised. So next question through chat is from Heidi Williams. In part one, you discussed how the non-spatial, non-dynamic treatment of mortality is somewhat mitigated by the fact that in non-ideal conditions, growth rate is slower, and so the fish stay in a life stage with a higher mortality rate for longer. If juveniles age up on January 1st, no matter what, this means that this treatment of mortality based on growth is limited to only fish in their first year. Is that correct?
Yes, generally that's correct, and I regret it. But there are certain bookkeeping things that make you do that. What I will say is that's one reason. One of our alternative baselines, if you remember the 5 baselines from the figure I kept showing, was we made mortality length dependent, and that means that it doesn't end on January 1. It depends how big you are, and so if you become an adult, you still would have the higher mortality rate because your length would be shorter. So that's a reason to smooth out that mortality and make it length dependent. It no longer is affected by January 1. And now other things change on January 1 for the juveniles who become age 1 adults. Some of their bioenergetic parameters may change, but the mortality would continue on the progression of slower growth is higher mortality in that version. By the way, there's a second thing I wish I had never done, and it's I blame California. The difference between calendar years and water years. If I tell you how many times I have drawn a timeline of how we output what year it is, you would.
I'm not listening.
I think finally Lee and Matt made us write it down, and Derek too. That's another thing that goes on. But yeah, so that's an example. You're right. But you can make it length dependent or a function of temperature, for example. And again, it doesn't have to change with January 1. What changes with January 1 is the life stage indicator.
Kenny, the other thing to do with the mortality schedule and the growth schedule is that, well, really to do with the growth schedule, is that when the fish mature, the model fish mature, they may not be able to produce eggs. Their fecundity may be 0 if they haven't grown big enough. So, and we had 2 ways of doing that. There's a knife edge one and a gradual one.
Yep.
They're a little different, but not hugely different. So, so even and that's, I think that's consistent. I think we understand a little bit about the growth process, that, the fish can keep on going. That the mortality is not necessarily a strong function of growth. It might be a strong function of length, but not hugely strong. But fecundity is a very strong function of size.
That's right. Yep.
Big effect on Lambda. Okay, thank you. The next question maybe good one. Okay, from Teddy Summer. So, Kenny, is there funding for continued refinement of the model?
So the project's ongoing for a while longer, probably through the summer, I believe it is, and then after that, there's nothing in place, and we have an ending at that point where the code's been updated, been recalibrated, quote unquote validated. There's a user manual or guide, and there's some interface that Lee and Matt's group have developed, and so that right now, and Matt may have other ideas, but I think that's where that stands. But I, as always, anyone who has questions about the model or something, they can just always contact me or or Matt, and then Matt would probably contact me. That, you know, I'm not retiring yet. It turns out I can't. So I'm still around, and you know, I love doing this stuff. So the funding is to get to a very nice stopping point and a soft landing, and then I don't know what happens after that.
Thank you, Kenny. Yeah. And let's go to Matt. Do you want to say something?
No, that was a good answer. Let's move on.
Okay. And Leo, raise your hand, Leo.
Hi. Hopefully everyone can hear me. Or
yeah.
So Kenny, thanks. One thing I liked your discussion on starting around lights 36 about what does it take to get lambda greater than 1. That's definitely something I've been interested in, because lots of people just look at effects on lambda, which is interesting, but I really I've been thinking about that question this past year a lot too, so might be interested to see how that progresses with you.
Mm-hmm.
One question I did have that I don't have a great handle on with this is this idea of the superorganism, I think you call it. So when you talk about things like mortality is length dependent and various movement of individuals, but what does that mean for a superorganism, and how does the model really, is there like regular individual organisms plus superorganisms, or what?
So very quickly, and I'm always happy to talk about super individuals, but very quickly, the way it works is we always have let's say 10,000 age 1 in the model and 10,000 age 2 in the model, but we give them a worth of how many population individuals they represent. So they may represent 150 population individuals, and what mortality does is instead of a binomial and we kill them or not, we decrement what they're worth based on their mortality, right? E to the minus m gives you the fraction surviving. So there's always 10,000 of them, but their worths are decreasing based on their mortality rates every day. And so when you stop for a moment, you add up their worths, you get the population abundance. The tricky part is how you start them from eggs, and we can discuss that. But they're all so that's what the super individual is doing. And why is that handy? Well, one is numerically we know how many we're going to have in the model at any given time. It's always the same amount of model individuals. So the bookkeeping becomes pretty straightforward, right? It gets complicated when you all of a sudden have a big year class, and now I have to make room for not 10,000 but 20,000. But then what happens to those, right? And then you can also run out of individuals if you kill them with a probability, right? So the super individuals are a way to always have the same number of critters in the model, but have their mortality reflecting their abundance through adjustments of their worth, we call it. But every output then has to be statistically weighted by their worth, everything.
And so, I understand that this could be kind of a computational convenient strategy, but in terms of like tracking individual lengths, which determine survival and all these other things.
Yep.
That's all done. Like it's just really slick and tricky how.
Yep.
So really the right interpretation is individuals, not super individuals.
It is, because what I did was, and it's a lot of work, but I did it, was every output that comes out of that model has already been adjusted. Because if you start having people make the adjustments post-processing, it's too tricky. You just end up introducing errors you don't need to introduce. So a lot of the code, not a lot, a good deal of that code is taking weighted averages, weighted sums, all those things to account for the super individual worths. So when you get it, it's already been adjusted when you look at it. because at first I was just outputting it and letting people post-process, and I was getting a lot of questions about it. So now I always put it in the code. But that's a really good question.
Okay, yeah, that's good. I just wanted sort of a conceptual help, but we can hassle with details if it comes.
Sure.
Thanks, Kenny.
Sure. Well, thanks for your help too on the stuff you've been sending.
Okay, two more questions from chat.
Okay.
Yeah. First one is from Sean Acuna from Metropolitan Water District.
Yeah.
Will you be using the following paper to help inform the movement parameters? The publication paper is from Ada Gross, 2021. Yeah. So
I have not. Either I looked at it and forgot, which is entirely possible these days, or I haven't digested it yet. So I'm curious to see what they did. So we're definitely going to look at it and see. I have not looked at it, but that's the kind of stuff that's coming out that is the reason why it was very important to update this model as well, right? But I haven't actually looked at that yet.
Okay, Kenny, I will get that paper and forward that to you. Yeah. Okay, next question is from James White, Fish and Wildlife. A lot of catch throw is so overgrowing with Algaria. It falls our sampling gear, making sampling so impossible that.
I think that's in response to Wim.
Yeah, already.
Oh, okay, sorry.
Nobody wants to sample there, and nobody wants to sample.
Okay.
To get over it. Figure it out.
Okay. Then we have.
Okay. I think that's the rest of them.
We have a question from Fred. Fred, your hand raised.
Hey, one more question for you, Kenny.
Sure.
And Wim and Matt and anybody else who wants to chime in. So with respect to your analyses looking at supplementation, I'm assuming that you're assuming that the supplemented fish, the cultured fish, behave and respond to things identical to the natural fish, the wild fish. Obviously, we don't know how true that is or not. Do you guys have any advice for people studying and working towards supplementation on the types of questions that folks can ask and generate answers to that will help contribute to the information you need to work this through appropriately with the model?
Oh, good, very good question. So that's a very good question. We can put it in the model because we tag we basically know every fish by name if you want to. And then we can say, well, you grow slower, you grow faster if you're I call them hatchery fish. I would look for things, and so there's an advantage here because you have them in a system where you can manipulate things. So I don't know what the practicalities are, but it'd be great to run some experiments where you take hatchery fish. I don't know if you can get natural fish, you're allowed or whatever, but see if you give them food at certain temperatures, certain amounts of food, do they grow differently, right? I think growth would be a big one. That's probably can be done. Mortality, of course, is tricky because it's the cylindrical cow right there. They're in a tank, but there are experiments that I worked on with leaf human, for example, where they simulated a predator as a pendulum coming at them and measured their responses. And we actually took that from millimeters and seconds and scaled it up to decades in a model with a series of calculations. So I think you could certainly do, I think you can probably do some experiments, and you probably have in the hatchery already, but thinking about now it's what are they going to do when we when we dump them in the water, right? And of course, the first thing is make sure the predators don't think it's a buffet, right? That's always a question, right? But what is there? I would think the first 5 to 10 days of life out there are going to be really important, right? And so I think you probably could do some experiments that would give us order of magnitude how to change things in the model. With a little bit of, I don't want to say magic, but maybe some pretty dramatic assumptions. But at least you could bound the problem, right? And I think that would be I don't do any experiments, so it sounds easy to me. But I think you can do things like that that'll help at least reduce some of the uncertainty about how different they might be, right?
Yep. All right. Thanks.
Sure.
Okay, thank you. Yeah, I did not see any more questions, so probably it's time. I would just thank our IT support, both Michael and Joe. Thank you so much. And if both of you, Kenny or Wim, you have final words, and then Matt will close the workshop.
I would just say, anyone has any questions, just send me a note or anything but Zoom. But we can even Zoom if we have to. But send me an email or something, or through Matt or through Lee, and I'm happy to talk about this stuff and see if how we can help use the model to maybe answer some important questions. Any words of wisdom, Wim?
No, I'll save them for next time. Can't think of it.
Okay.
Yeah. And we're already 7 minutes past when we said we were keeping everybody, so I'll just thank everybody for being here again. Matt Young, yes, it'll be available. Lee can get a hold of you about when.
Yeah. Yeah.
And other than that, have a good lunch, and we'll see you again sometime this summer.
Thanks a lot.
Thanks, Kenny.
Yep.
Thank you.
Thank you, everyone. Bye.